just introduce Reem in the talk. So, I think we originally met at AIMS, the African Institute of Mathematical Studies out of Muizenberg. I think I was doing my master's at the time. Reem has always been like a solid member of the Town Machine Learning community. She stuck around, did her studies, postgrad studies at Stellenbosch, and she's always been sort of attending conferences like Deep Learning in Daba. She's been doing a bit of research, and this is one of the papers that she found quite interesting, neural ordinary differential equations. She'll take us through the paper and some of the ideas that are introduced. We sort of found this to be like a very interesting topic, and we grappled with some challenges coming to grips with what was really going on here. So I think she'll lend a bit of expertise. And before we kick off, I'd really like to thank Whereby for sort of sponsoring this virtual event for us, giving us this space and this platform to be able to connect. So with that, Reem, please take it away.
Thank you for the nice introduction. I'm very happy to be here with you, and I hope that we can all benefit by the end of this session. Okay, so my name is Reem, and I'm interested in machine learning in general, and sometimes when I stop by some topics, I find them quite interesting, so I either write about them in a blog where friends of mine and I write some articles about machine learning in Sudani dialect. I'm originally from Sudan, so that's kind of information sharing, one way of information sharing. So I'm happy to be here with you so I can share with you some of the information that I got while going through a neural ordinary differential equations paper. I'm currently a data science intern at Manubi, Africa. Okay, so today I'll go through, as I said, the neural ordinary differential equation paper. I will give a bit of a background, and then we will see some basis of artificial neural networks, and then we will move to residual neural networks, and then we will see how residual neural networks is related to ordinary differential equations, and then we will take it from there and we will see how all of the previous points motivate neural ODEs. Okay, so first of all, we need to start about what's the paper about. So from now on, we will call ordinary differential equations ODE in short, okay? In short. Okay, so the neural ODE, or in some articles, you might find it written as ODE-net. It's one of the machine learning models that uses ordinary differential equations to find the approximation function, as if you all know that in artificial neural networks, we are trying to approximate some functions by applying some algebraic rules. What makes this paper very interesting is that it assumes, or it claims that it doesn't need to define the number of neurons or the number of layers if you want to build the architecture of that machine learning model, okay? The authors of the paper also proved that the training process using the ordinary neural networks was slower compared to other models like multi-layer perceptron or residual networks, but it was very fast on training compared to them. And what makes it more interesting is the fact that it uses a new mathematical approach which wasn't used in the scope or the field of machine learning. And we will also see how neural ODEs are memory efficient compared to other models. Okay, so to give a bit of a background about artificial neural networks, we know that in ANNs we normally have input layer, and we have several hidden layers. It could be one or more. And then we want to get to our final output layer, we can think of this as the architecture that takes our input and try to convert it using some computations into some output, okay? So every layer contains of several neurons, and the main idea or the main goal of these neurons is to apply some computations. These computations are basically some matrix multiplication. Sometimes we apply some vector addition and so on. So we can look at the algebraic form on the right-hand side of the slide, where H1 in this case represents the first hidden layer that takes our input and multiplies with some weight and then adds some bias. And of course, all of this is passed to our F, which is a function of, let's call it the activation function, that give us the output of this hidden layer. Now we will when we go to the second layer, we will also apply the same concept and so until we reach our final layer. Okay, so in theory, if we can think of these computations, we can easily say that every input can be possibly moved to a certain output or mapped to certain output by stacking more layers or adding more computations in the middle, okay? However, this concept wasn't true, or we can't apply this in practice, because remember that the output of the final layer, if we think of it as a classification problem, is highly influenced by the architecture of the artificial neural networks. And in this case, it will be influenced by the number of neurons and the number of layers that we have. And of course, all of these will lead us to some problems. Of course, we don't want to have a very naive architecture where we have an underfitting case. Also, we do not want to stack multiple layers and add unnecessary computation, so we can have some overfitting in our data. Okay. There is also another problem, which is the trade-off between the accuracy that we want to get and the complexity. And in this case, it will be the time complexity and the space complexity, or the memory in this case, okay? So for a long time, machine learning researchers have been, or practitioners have been trying different architectures, and they were interested in finding the optimal parameters that could work in sufficient amount of memory and in sufficient amount of time. So by this, they have to try several times, trying different parameters until they get to the optimal parameters. Okay? Now, in 2015, there was a new concept introduced to the machine learning community, which is called residual neural networks. So as we said earlier, we do not want to have many unnecessary computations. So the residual neural networks is the new type of machine learning that introduced what we call the skip connections, okay? So skip connections are basically adding the identity or the same input to the second layer in our architecture. And in this case, for example, if you look at this figure on the left-hand side, we take our input, we multiply it by some weight, and then we add bias, of course, and then after that, we apply our activation function. This is one layer in a regular artificial neural networks or deep neural networks, right? Now, to move to the second layer, we normally have to reapply what we did in the first layer. But in this case, in residual neural networks, what we did is we took this output, which I will call here by f of x, and then we multiply by some weight, and before we pass our final output to our activation function, we add our x as an input again. And then after that, we apply our activation function, which happened to be, in this case, ReLU function. Okay? So the main idea of skip connections that was introduced in residual networks resulted in having a higher accuracy, right? Because now we are not, there are some computations that were skipped by applying this skip connections, or when we add the identity vector to our output. Okay. Now the final output that will be passed to our second or the following layer would be this function, which is f of x plus x. So if you see here, our output, or the which will be the input to the second layer, which is in this case x of t plus 1, will be equal to our previous input, which is x of t plus some function that is applied on x of t. Okay, please keep this in mind because I will be referring to it in the upcoming slides. Okay, just to give a quick comparison between the regular artificial neural networks and residual networks architecture. As I mentioned earlier, in a regular ANNs, what we will do, we will take our input x, we multiply by some weight, and then we pass our output to activation function, and then we will continue this again and again, which will take the output as an input to the following layer, multiply by the weights, and then apply activation function. This is our regular artificial neural networks. When we stack multiple blocks of this layer, we will end up having a deep neural network, okay? Now, on the other hand, if you look at the right-hand side of the slide, you can see that we are applying the skip connection. So before we move to the second layer and apply our activation function, we are taking our input, which is in this case x, and add it to our f of x, which is the result of the previous layer. Okay. Now let's see how residual neural networks motivate the neural ordinary equations. Now, if you remember from the slide, we knew that x of t plus 1, which is the input, or the input for the second layer, is equal to the input of the previous layer, which is the first layer, plus some function of the output of the previous layer. And if you multiply this function, your function f of x, by 1, this gives you exactly the Euler method, or the formula for Euler method. Now, I will give a bit of background about ordinary differential equations, so we can make it easier for us to understand the neural ordinary differential equations. Okay, so as we saw on the first slide, or the second slide, that the claim was that neural networks or neural ODEs did not, or doesn't need, an identification of neural number of layers or number of neurons in this case. That means we are not moving some discrete values. Okay. The neural ODEs thought of the problem as a continuous problem. So instead of solving some discrete values, because we are moving from one layer to another, we will rather think of it as a continuous problem, and then we will try to optimize, and we will try to approximate our function that takes us from any input x to any output y. Okay, let's see how can we convert our problem from discrete problem into continuous problem. Okay, First of all, we know that the differentiation of a function, well, in this case, I will be just looking at the discrete version, is given by this formula, right? I hope that you remember this formula from, I don't know, maybe high school, okay? And then it's given by some value y that is changing over time. That's why we are using dy by dt. And this will be defined by the change in the value of y, which is here defined by y, denoted by yt plus some change, which is in this case delta, minus the earlier system of the state, which is in this case y of t, and then everything will be divided by delta, which is the change. Now, if I rearrange this equation, we will get to our yt plus delta, which is the new state of the system. If you can think of this as a system of equations that changes over time, the new state of the system will be given by the old state plus some delta change multiplied by the change of the function, okay? Now we know that in the artificial neural networks, the following state, which I will call in this case by ht plus 1, is equal to some function that is parameterized by the previous output and some weights, right? In the residual neural networks, the following, the output or the input for the following layer, which is in this case ht plus 1, it's not only equal to f of ht and some w's. No, we are also taking into account the same input to the function, which is in this case h of t, okay? Now, if you look at this value here, what we are trying to do, we are trying to find the similarity between our residual neural networks and what I mentioned earlier about Euler's method, okay? Now from here, this will be equal to the differentiation formula of our function yt plus delta, but then if you took this delta and replace it by 1, you will get exactly to this formula, right? Just compare the formula in red with this one. Now from here, we could see that this rate of change is nothing but the same function of the previous hidden layer, right? It's written here in blue. You can look at these two. And we know that this function takes not only the input of the previous layer, but also some parameters that need to be optimized, which is in this case, W. Okay. Now, to put it all together, what we want to do, we want to look at the function not in the discrete version, but in the continuous version. Now, from here, to move from this discrete version of the function that we got into a continuous function, we will just introduce our new term, which is in this case, t. Okay? So we will get to this point where the rate of change for the value y doesn't only happen to be with respect to some values w's, but also it changes with respect to time, okay? That's why we received this point. In fact, this is the point that we want to get to, so we can use some ODE solvers. Let me just mention something before I move further. This final output is called an ODE, ordinary differential equation. Why? Because we have one variable, which is in this case y, that changes over time, okay? We call this ordinary differential equation. And the main idea of the article or the paper is how to use the, how to solve the ordinary differential equation. So in this slide, mainly what we did, we wanted to make sure that we can replace our f in the residual network with this change, rate of change, dy by dt. And all of these steps is just to do that. Okay. So is everyone following? Anyone has any questions so far? Okay. Okay. Okay, let's move on. So, a quick reminder, what we did from the beginning of the presentation up to now is we firstly saw the algebraic formula of artificial neural networks and how is it, how every hidden layer takes the previous, or it depends actually on the previous hidden layers. And then we saw that stacking multiple hidden layers does not solve the problem of, okay, doesn't solve any problem, and then we can't reach to the highest accuracy just by stacking multiple hidden layers. Why? Because we saw that it has different problems. One of them is the overfitting, and then the other one is we do not have enough time to run all the complicated models, and also we do not have enough memory to do so. Okay, after that, in 2015, there were some researchers introduced the concept of residual networks. What we did in residual networks, instead of applying all the computations that we do when we stack different hidden layers, what we did is actually we choose only to apply one hidden layer and then skip to the other one by introducing the new term, which we call the identity. So basically what we did, the block of two hidden layers becomes only one hidden layer, and then we skip the following one. So in this case, the neural network will focus on some of the hidden layers and will apply less computations compared to the ones that used to be applied in a regular artificial neural networks. And then from there, we saw that the formula that's used in the residual networks is nothing but the Euler method with a coefficient of 1 in the side of the function, right? And then what we did on this slide, which, okay, I promise, this is the one that has the heavy math, but everything else will be easy to absorb. The only thing that we're trying to do in this slide is basically to see how can we convert the second term in the right-hand side of the residual network into a differentiation term, right? Where we focus on something that changes over time. And in this case, you can think of it as the final output, okay? This is what we did so far. Okay, so let's see how can we solve an ODE in general. So solving an ODE in Python, well, okay, I don't know about other languages, but I think all of them, they do have several functions that used to solve numerical problems, okay? In general, if you look at the right-hand side, let's assume that we have function y that changes over time. And this function is given by this equation, 3x squared plus 2x plus 1. And we want to find its function. This is exactly what we do. Look here, what we did, we actually changed this part with this differentiation part, right? And then what we want to do in ordinary differential equations is to get to this function, okay? So to do so, there are two ways to solve any ordinary differential equations. You can solve it either analytically, and of course this is by applying some mathematical properties, using some mathematical formulas and applying some properties, but it turns out that not all of them are solvable. Not all of the ordinary differential equations are solvable by hand, or let's say analytically. And there's also another way to solve them, which is numerically. Numerically is basically by introducing some methods that use to approximate this derivation. One of those methods that used to approximate these values is called Euler Method, which I mentioned earlier in the presentation, okay? Euler Method is not the only solver that approximates this rate of change. There are many of them. And in this case, or let's say in the case of the paper, they just used what we call ODE solver. ODE solver is a function that approximates the derivative of some given function by integrating some values. Well, I don't want to get into the deep details, but let me just go through the code quickly with you. Okay, so first of all, in order for us to work with the ODE solvers, we have to call our ODE end function, which is defined in the integrate under SciPy library. Okay, we define our function that we want to approximate this function. We define it by dy dx. And now in order for us to call our ODE solver, we need to call our function. Remember, ODE int is the function that approximates some other function, okay? So it takes our main function as an input, which is dy by dx. It takes some initial values, which in this case I use 0, and then it also takes some rate of change, because remember, I think this should be x. This should be x, dy, yeah, dy, this should be x, dy by dx. Okay, so it should be dy by dx. Okay, this x is the dependent, what's the, sorry guys, dependent. Independent is the one that doesn't depend on the other. So, okay, so this x is the independent. So this x has several values. Whenever I plug in here one value of x, I should get some value for y, okay? So ODE int takes the function, takes some initial values, which is in this case 0, and takes some parameters or range of values for our independent variable, which is in this case x. Remember, in the or if you look at the previous line, we can see that x is just 10 values that ranges between 0 and 10. Now, if you look at this equation here, and if you want to find your function y, what will you do? You will divide here by 3, and then you increase here the power by 1, and then you will divide here by 2, and you increase the power here by 1, and then this one will be equal to x, okay, and then plus some constant, right? In this case, the original function is given by this function, which is defined as y of actual. Now, what we want to do, we want to see if our approximator, the ODE int, can give us some exact value or similar value to this actual equation, right? And now if we plot these two, we can see now, I don't know if you guys can see, but the dotted line is the actual values. The blue one is the predicted values. They are actually very, very close. there is some small change between them. The approximated value, of course, this ODE int is just an approximator. It might not give you the exact solution, but you want to get as close as possible to the actual value, okay? So here you can see that some of the predicted values and the actual values, and of course, because here we have this value of 7, you might realize that there is a shift of 7 between these two values. But if you look at the second one, for example, you can see that on the first few digits, they are exactly the same except in the last digit. This one is 2 and this one is 6. Well, and there is also some difference in this one, and so on. These are just some of the values. So from here, what we saw, we now know how to solve or how to approximate how to approximate our dy by dt. This is what we want to do in this slide. Okay, let's just put everything together. Okay, well, it's not actually very difficult. The thing that makes it easy is if we look at the right-hand side and then we move to the left-hand side and then we try to connect the mathematics with what we see on the figures, okay? So, a reminder again, what we want to do, what we did in the previous slides is basically we knew that our function is equal to some rate of change, which is given here by dht by dt. And it turns out that this value here is nothing but the exact value of hidden state at some depth t, meaning this t now will be something similar to the layers that we used to have in our ResNet, okay? And now, in order for us to get to this function, remember what we want to find is the value at each hidden state. If we want to get to this ht, what we want to do is we can just rearrange this by multiplying this term by dt, and then by integrating both sides, we can find that the new value for ht is given by some integration for the previous hidden state. Okay. Remember that in numerical solutions, or in the previous slide, we saw that the ODE approximator takes also something called initial value, which is in this case will be the value at the beginning of the time will be our input to the neural network. If we think of a classification problem, this initial value, okay, let's think of a MNIST dataset. So in MNIST dataset, we have images for different numbers, and then what we're trying to do is to classify those numbers, or to see if this image is 0 or it's 2 or 3 or whatever. Now you can think of this initial value as the image of the 2, okay, or 0 or any other number. And then your final state, what you want to get to is the class or the 2, okay? So what you are doing, you are moving from T0 to some T1. The value of the hidden state at T0 is given by your image, okay? And now, in order for you to move to the second hidden state, you have to apply some function f of t. Now, in order for you to do this, is basically you call the ordinary differential equation solver. This ODE solver takes your function that you want to approximate. It takes your initial values. Okay, in this case, we pass our T0 as initial value and where we want to get, which is T1. Remember, it will be equal to the x's that we have yeah, the x's that we have in the x's, yeah, these will be equal to the number of the steps that we have in our previous example, and these w's are our what do we call them? The weights that we want to optimize, and this is our function, okay? Some initial state, some steps, weights that we want to optimize, and some function. If we solve this by an ODE solver, we can move from this state, h of t naught, to h of t1. And then we will just, if we want to apply another step, we will just call this another time, and we will call it a third time, fourth time, and so on. As we saw in our previous example, because we have 10 steps, that means we take our initial value, which will be 0, and then we approximate our function using the ODE ent, which is the function that approximates our dy by dx. And then after that, we get here, let's say, to this point, and then when you move to the second one, now you have mu x, which takes the previous input and then apply this value approximation, and so on. And then you will continue doing that until you finish all the number of steps that you have, okay? Now from here, we knew how to move from one step to another. Okay, this part here is equivalent to the residual networks. So what we did exactly, we just replaced every block of residual network by ODE solver. Okay. Now, if we think of the back propagation and how can we move back in time, we can think of it as a function that is parameterized by not only the time or the steps that we took to get to our final state, but also by our W's, which are the weights. And in this case, they found that this setup, or when we apply the loss function to this ODE solver, we actually get to know something similar in numerical methods, which is called the adjoint method. And the adjoint method has some formula that it has been used to solve any function approximation backward in time, and it's given by this equation. Okay? So what we did so far from the previous slides, just from ODE, from what we saw in the previous two slides, that the neural ODE function takes into account the function itself that we want to solve, the function that we want to solve, the steps in time, and some parameters that we want to optimize. And in this case, everything will be dependent on our initial state. What we saw here is how can we visualize the steps that we are taking from any initial step, which is in this case the image of the, let's say, the image that we want to classify, and then how can we get to our final solution, which will be our Y. And then in order for us to do this jump, we have to apply an ODE solver. Now, in order for us to apply the back propagation, we will just refer to what we call adjoint method that takes the final output of our function and apply some adjoint states backward in time. Okay. So let's see the main difference between residual networks and ODE networks in terms of code, in terms of the code. Okay, So we know that in both residual networks and ODE networks, we are referring to some function. Our function in this case it's nothing but our input that is given at any specific time. Let's say if we are in the first step, we are just looking now at the image and some values that we want to optimize, which is in this case our W's. In the residual networks, we are moving through time, where every output or the output of any state or any layer, which is the input for the following layer, will be given by the same input plus the function of that input. And in this case, we will be retaining our final output, which we got here. If you look here, our ODE network, what it does, it calls instead an ODE solver that takes our function, which is our neural networks here, and it takes our X, which will be our initial value, and it takes the steps that we want to perform, which let's say that we want to move from any step 0 to, from any initial step, we will call it 0 to 1, and some W's that will be optimized. I hope this is clear. Okay, so after all of this explanation and a replacement of, let's say, a very long history of computations that machine learning practitioners used to apply, and then we just try to find some similarities between the concepts that we had and the concepts of numerical methods, which were existed they were like existed in a very long time now. I don't know how much, but I think like numerical methods have been like known for ages. Can we now see a difference in the final output? Can we avoid the problems that we saw earlier? Well, if we can just compare the performance of the ODE networks and residual networks and any other methods, you can see here on the left, we have this MNIST dataset, which has these different images for several numbers. We apply some function in the middle, and then what we want to get is these classes, okay? So if you look at the table on the right, you can see that the ODE networks, they did not actually have, well, they have smaller test error compared to the rest of these methods. MLP, ResNets, Ranjakota networks, which I didn't cover, is not part of this presentation. And now if you compare the number of parameters that has been used in all these methods, the ODE networks has small number of parameters. And also if you look at the memory, it has less memory compared to the rest. Okay? The main reason that this function, RG, Ranjakota networks, has a small number of parameters also is that because it's also uses some numerical approximators. Yeah? Yeah. Yes, thank you so much for listening, and I hope that you understood what I was trying to explain. I'm quite sure that things might not be very, very clear or crystal clear from one time, but I hope that it just gives you a background. So if you want to go and look further about the method and the new approach that they have been following to solve some problems, you might be able to do that with more comfort.
Reem, thank you very much for the talk. I think that was actually very clear. So I think when we originally sort of saw the paper and had a look, it was tough to sort of to really understand what was going on. But I think you really presented it quite well and you made it clear what's going on there. Thank you for that. If anybody has any questions, please post them up in the chat, and then we'll sort of be able to get into them. Yeah, I don't think I've got any on my side. I think you addressed everything which was sort of eating me up inside about this paper. Tuso, do you have any questions that you'd like to throw into the mix? Or anybody else for that matter?
Reem, can these networks still take advantage of GPUs when you're doing the ODE solving?
May you please repeat your question?
Yeah, sure. Can you still use like GPUs and like the neural network architecture like that to optimize the neural networks, since it's no longer being done through like dot products and stuff like that? Or I'm not 100% sure on how it actually is calculating the weights and stuff.
Do you mean to optimize the weights in the neural networks?
Yeah.
I'm not actually 100% sure about how will that be addressed in this case. But I think it uses less memory because of applying these numerical methods. So in that way, we might not, I don't know, I don't think it's necessary to use weights as we use them in our regular neural networks. I'm not sure.
Yeah, I think it's quite a tricky question. I think that there are some libraries that give you sort of general mathematical ability on GPUs. So certainly you can do things like solve SVMs and a bunch of other things. So if there's a library that allows you to apply a numerical solver over a GPU, that would, I suppose, answer your question there too. So, but yeah, I think that's like it's a really tricky thing to know. Yeah, unless you spend a lot of your time in the numerical method space.
Yeah, maybe next time. I need to go through the paper again and again to fully understand how things working, because they also have some problems, and it has been solved in more recent papers that were published in late 2019. Yeah.
Sure. Do you know what those problems are that they were trying to address in the sort of the new updates?
Yeah, I think one of them is the time, because remember in the paper they didn't mention how would they differentiate between the number of layers and the time. So from what I understood from the paper is that in order for you to use ODE solver, you have to give it some, not only the initial values and the function that you want to solve, but also you have to identify the the time steps, which I think in this case would be equivalent to the number of layers. But it won't be like solved in discrete way. The ODE solver might try to find smaller steps in that range of values.
Yeah, I hear you. I mean, I guess that whole concept is quite a mind-bending concept to really wrap one's head around, because this whole analogy of going from a traditional neural net, which has discrete sort of steps, sort of as I guess indicated by these various sort of like chains of computations, and then obviously chains of like derivatives that you calculate, versus ODE net, which it seems like takes steps across that curve or that space of different sizes. That's quite a tricky idea, especially then when you sort of involve this idea of how many steps could it be taking. So you might have two networks, a regular neural net that takes 10 steps in discrete fashion of the same size across the curve or across the space, whatever it may be. And then you have an ODE net that also takes 10 steps, but the steps of different sizes, and they can take place in different places. And that then creates this continuous versus discrete sort of interplay or relationship. And yeah, it's a very sort of like, well, anyway, to me, it's a very new idea. And I think this paper really inspired me to think more along those lines and try to figure out what that actually means, especially in the context of actually solving some of these problems. Like if every method we're using always takes a discrete approach, what are you missing by not taking the continuous approach and taking steps of different sizes? So I think I also probably need to go back to that paper and investigate it just a little bit more.
They also introduced some concept of tolerance, which should be, or okay, it's one of the inputs to an ODE solver. Of course, not all solvers are like perfect. Like for example, Euler's method could be one of the simplest way to solve an ODE. And if you, for example, take a small tolerance, the function might take longer time than taking high tolerance, because if you allow the approximator to have multiple errors, it doesn't have to iterate through the function again and again to optimize it. So I think that wasn't fully covered in the paper. There was actually a very interesting talk that was given by David, one of the paper's author at Vectors Institute, where he described in details, I think five or four things that he mentioned. They were like wrongly mentioned in the paper, and he was corrected the paper, in 2019, I guess.
Yeah.
So I will share with you all these details, maybe if any one of you is interested.
Sure, thanks. So I think what we'll do, what we've been doing lately with all the talks is we'll create a channel for you on our Slack, and we can share the slides in there, and we can also share sort of additional resources. And then if people have questions, they can sort of just pop those questions in there, and then you can sort of like pop in and sort of engage them at that level. It doesn't seem like we've got any questions in our chat from anyone. So I think everybody, I think your talk did what it was meant to do. It sort of gave everyone a deep understanding of the material. Either that or it just confused everyone and they're not sure.
I'm sorry. I tried to be like, okay, in order for everyone to understand, we have to go a little bit deeper than what they mentioned in the original paper. That's why I had to go through all this math. I'm sorry if I confused anyone, but okay, the only one thing that you can take from all this talk is that you can replace the res network block by something called ODE solve. That's it. If you get that, then you're fine. You're good.
Yeah. No, I think it is a success. Sorry. So I mean, look. Thank you very much, Reem, for the talk.